Now let me explain about the Coulomb's inverse square law. Now let us consider two charges Q A and Q B. They are separated by the distance r. They are separated by the distance r. Okay. So, according to Coulomb's inverse square law, it is given by F is equal to, take down, is proportional to, you can have Q1, Q2. Let me consider two charges. So it is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So you can combine these two. So F is equal to, or F is proportional to Q1, Q2 divided by R square. And here F, this proportionality can be made equal by including a constant K, and that constant is 1 by 4 pi epsilon naught, okay, into Q1 Q2 divided by R square, and this is called Coulomb's inverse square law. Where, let me consider a charge Q1, another charge Q2. The distance between them is R, right? So Q1, Q2, 2-point charges. The distance separated is R. So it is inversely proportional to the square of the distance. And epsilon naught is the permittivity through free space. Permittivity through vacuum or free space. And you should know there is a term called relative permittivity. So here, relative permittivity. So here it is equal to E divided by E naught. It means E epsilon, not E epsilon, permittivity of certain medium, and this is through vacuum, permittivity through vacuum, and this is relative permittivity. Therefore, epsilon is equal to epsilon r into epsilon naught. What is epsilon r? Relative permittivity. Epsilon naught, permittivity through free space, that is vacuum. So what about this force? This force is through certain vacuum. If it is through medium, a particular medium, let us represent a medium. So in that case, it becomes F, certain medium, is it not? So 1 by 4 pi epsilon into Q1 Q2 divided by R squared. And we know epsilon is equal to epsilon r into epsilon naught. So we can introduce Fm is equal to 1 by 4 pi epsilon r into epsilon naught into Q1 Q2 divided by R squared, right? Now let us analyze the unit of this constant 1 by 4 pi epsilon naught. Have you noted down? Right. Now let me consider this flashcard. So here, as I already mentioned, F is proportional to Q1 Q2 divided by R squared, and F is equal to K constant, and that constant is nothing but 1 by 4 pi epsilon naught. Now we are interested to find out the constant here. Therefore, K is equal to F into, you can interchange this. So F into R squared divided by Q1 Q2. And what is the unit of K here? F is Newton. R squared means the distance between them. So meter squared. And what about Q1 Q2? Q is Coulomb. So Coulomb squared. Therefore, K is equal to Newton meter squared per Coulomb squared. That is Coulomb power minus 2. And this K value is given as 9 into 10 power 9 Newton meter squared into C power minus 2, or you have to call it per Coulomb squared. So you have to remember this value. So what is the value of 1 by 4 pi epsilon naught? Which is nothing but 9 into 10 power 9. Okay? Never forget this value. And what is this epsilon naught? Which is nothing but the permittivity through free space, and it is the value 8.854 into 10 power minus 12 Newton per Newton meter power minus 2, then Coulomb squared. So remember this value and also the unit. And you know force is, F is nothing but the force of interaction between the two charges, and Q1 Q2 are the charges. Of course, the R is the distance between these two charges, right? Got it? Now let us proceed. Electric field. Electric field is the expression E is equal to F by Q. So which is nothing but the ratio between the electric force and the charge. So E is equal to F by Q. We have got already F is equal to 1 by 4 pi epsilon naught into, assuming that Q1 is equal to Q2, it has got equal charges. So in that case, Q squared divided by R squared. Now E is equal to 1 by 4 pi epsilon naught into Q squared divided by R squared divided by Q. So the Q can be cancelled. Therefore, E is equal to 1 by 4 pi epsilon naught into Q by R squared. So what is the force? Force is 1 by 4 pi epsilon naught into Q1 Q2 divided by R squared, or Q squared divided by R squared. Whereas the field is simply Q. So 1 by 4 pi epsilon naught into Q by R squared. So that makes the difference. And let us work out the unit for this. So E is equal to, we know this K, 1 by 4 pi epsilon naught is nothing but K, and the constant value is 9 into 10 power 9 into Q by R squared. So this much of Newton meter squared per Coulomb squared into Q, that is Coulomb, divided by R squared. So you can cancel everything, and therefore E is equal to what? Newton per Coulomb. Okay, and this can also be derived from this equation also. So Newton per Coulomb. So what is the field, unit of electric field? Newton per Coulomb. Okay. So let me recap. I was already discussing about the electric field lines. So what about electric field lines? Electric field lines are continuous curves. They emerge from positive charge. They end at negative charge. There is no break. It's a continuous curve and it is tangential. They never intersect each other. So these are the key points as far as electric field lines are concerned. Okay. Now, let me explain about the electric field. In fact, this electric field has various nomenclatures, so you should remember all these things. E, that represents the electric field, and as a vector also, E vector. Electric, it is also called electric flux density. Take down electric flux density, and this is also known as the electric field intensity. So this is given by the expression 1 by 4 pi epsilon naught into Q by R squared, and it's a unit, as I already mentioned, Newton per coulomb, and this can also be represented by the vectorial formula, that is 1 by 4 pi epsilon naught into Q by R squared into R cap, where R cap is the unit vector or the distance. So R cap, unit vector, we know the vector is represented with an arrow mark at the top. So R vector. So R vector, and this represents the, what do you mean by vector? It is representing both magnitude and direction, right? So when you are very specific about the magnitude alone, in that case you can introduce the modulus of vector R. When I say modulus of vector R, it represents only the magnitude, is it not? No direction is involved here. Therefore, modulus of a vector can be simply represented as a scalar one. You can simply put R also, okay? And you should note down this formula, that is R cap is equal to, that is vector divided by R vector divided by the modulus of that vector. Okay, so remember this formula, and that is why we have replaced here. Okay, next, as I already mentioned, the electric field is also called flux density, electric flux density. What do you mean by electric flux density? Flux is nothing but a force line, electric force line, electric field lines or force lines. So the flux divided by A. So phi represents, this is called phi. It should be termed as phi. So phi is equal to electric flux. So how many, in fact, let me consider a point charge like this. As we know, the electric field lines will be emerging out of plus, is it not? And closer to the plus, the point charge, the field will be stronger, is it not? It is something like that is throwing a torchlight. When you throw the light from the torchlight, near the torch, it will be brighter. As we go far, it will be, the intensity will be less, is it not? So similarly here, near the electric charge, that is the charge, point charge, the field is stronger, and as it goes away from that, it becomes weaker, and that is why we call strong field nearer to the charge, and away from that you are experiencing a weaker field where the number of lines divided by the area of cross section here, will be less, is it not? Naturally, okay? So the field density will be less here, and that's why we call it weak field, whereas this one is strong field. I hope now you should be able to understand the difference between weak field and strong field. And I want to give you some other that is aspects about the vectors so that you can understand better. So here we have got some unit vectors. So starting from the origin, that is towards x-axis, you have got the unit vector, and that is represented as vector I, unit vector. So I cap. And similarly along y-axis, j cap, along z-axis, k cap. So I cap, j cap, k cap are the unit vectors along x-axis, y-axis and z-axis. So as I already mentioned, the I cap is nothing but the x vector divided by the modulus of x vector. And this can also be represented as x vector divided by x. Similarly, j vector, that is y vector by y, k cap, that is z vector divided by z. Okay, so these are about the unit vector, so that it will be useful during the derivations of some important aspects about electric field and electric forces, right? Now let me explain about the charge density. Let me talk about this charge density. Before that, I would like to give you some formula so that you can understand better. So, linear charge density. Linear charge density means that is you have got the straight line where how many charges are organized or arranged. So, in that case, lambda, it is represented by lambda, which is nothing but the delta Q divided by delta L. The difference. And the surface charge density is given by sigma, which is nothing but delta Q divided by delta S, where delta S is the small surface area. And what about this small length element? You can call it length element also. So for shorter element, how many charges are there? And the volume charge density is given by rho. So this should be written like this, rho. So rho is given by delta Q divided by delta V, and delta V indicates the small volume change. When they are represented by dq, it is called infinitesimally small, and dl infinitesimally small length element. Similarly, dq divided by ds, and similarly you have dq divided by dv, the volume element. This is surface element, this is length element, okay, and for which what is the charge? So dq, the small charge. So now let me illustrate this. I got some let me take a conductor PQ. So here I am taking a small length element, and for this small length element, what is the charge possessed by that? So that is called dq by dl. Do you understand? And this is called linear density of electric field, okay, linear charge density. And what about this? This is some surface area. I am taking one surface area like a graph. I am taking 1 square centimeter, square mm, and that is the small surface area, okay. Now when we are able to calculate this one, we can easily integrate the entire thing, is it not? That is the very idea. So delta S, so dq divided by ds, or delta q divided by delta S, that is the small surface area, that is area element. And in this case, the volume, a bulk one, where we can consider a small cubical volume like this, okay, and it can be delta V, is it not? The small v, delta V. And what could be the charge possessed or accommodated in the smaller volume? That is called dq by dv. So this is called the volume charge density, okay.